Hi folks, and welcome back to Physics with Captain Ron. I'm making this video to be kind of an introductory video about a concept called acceleration. So we're going to kind of study the motion of this green car here, and I've put a coordinate system in the problem right here. And again, you can put a coordinate system wherever you want in a problem, facing whatever direction. I'm going to use the x coordinate here to discuss the location of that car, measured to this dot here on the car. And we're going to look at a couple of different cases here. We're going to start with what I'm going to call case one, where the motion diagram for the car, so just a little reminder of what this means. You imagine snapshots in time. I like to think of a digital camera taking pictures. Click, 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 click. It's important though that the clicks be equal time intervals. And then superimpose all the pictures. This dot, rather than redrawing the car over and over and over, it might look something like this. Click, 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 and so forth. And what's important to note here is that the delta x's, the distance the car is moving, this distance, and then this distance, and then this distance. In this picture, you'll notice there's no significant change. I say significant because I drew those by hand, but there's no obvious change in those delta x's. And that means that the average velocity of the car is not changing because the delta t's are the same and the delta x's are the same. Right now we're going to talk about what that looks like graphically. So if we were to plot the velocity of the car against time, it's a pretty boring graph. Right? The car is moving at some value. It doesn't matter what it is. I'm just going to put that here. Maybe it's 2 meters per second, maybe it's 7, it does not matter. I'm just going to put the initial here. And then a second later, the velocity is the same. And then a second later, the velocity is the same. So we're going to get a graph that looks like this. Now, if I may take a moment here, the reason these numbers are positive is entirely because of our coordinate system. I've got the positive x-axis pointing to the right. Inherently, what that means is I've defined it this way as positive. And the car is moving in that direction. So that velocity, right, could be considered positive. Had the car been moving in the other direction, this would be down here. Anyway. Now, if we think about slope, well, if I pick any 2 points on this line, we're going to get zero slope because there's no rise. Right? So it's kind of a boring case to talk about. So this car is moving at what we would say is a constant velocity, and the slope of that velocity graph is 0. Right now, we're going to look at another case. I'm going to call this case 2. Where the driver, hits the gas, actually speeding the car up. Now, it's important to realize what would happen to our, how our diagram would change. So picture the digital camera going click, 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 taking pictures. Right, so our first click, this dot moves to here. If the car is moving faster, then the next dot is going to move that same delta x and a little more. And then the next dot will be like the previous delta x plus a little more because the car is moving faster and faster. Again, if the case 2, right, driver's hitting the gas pedal. So now, when we draw our velocity graph, a second later, the car is going to be moving at a slightly higher velocity. And a second later, a slightly higher velocity. And a second later, a slightly higher velocity. Now our graph looks like this. It now has a non-zero slope to it. Now whether or not it's perfectly linear is not important for the discussion. For now, let me just assume it's pretty much linear, or at least approximately linear. And we start considering the idea of slope. So if I pick any 2 points on this graph, doesn't matter where they are. The horizontal distance here is my run. Right, that's going to be a change in time. The vertical distance is my rise, and that's now a change in velocity. So our slope, which is going to be change in velocity over change in time, is now going to be some number that has units of meter per second per second. And this slope is called acceleration. define acceleration like this. I'm just going to put A, right, for acceleration is defined as the rate of change of velocity. Acceleration, like velocity, is a vector quantity. This car, you'll notice that the slope is positive, meaning that the car is accelerating to the right. If the driver had applied the brakes instead of the gas, this graph would look something like this. The slope would be negative, indicating that the car is actually accelerating this way. Now, one of the things I'd like to warn everybody about right now is this. Do not make the assumption that positive accelerations mean speeding up and negative accelerations mean slowing down. That's not the case at all. The plus and minus signs have directions relative to some coordinate system. So this green car is moving to the right. If the driver gives it the gas, the car would be speeding up and the acceleration is this way, and that would be considered positive. That is true. With the car moving to the right and the driver hits the brakes, right, the velocity graph would look like this. And the car would be slowing down and the acceleration would be negative, which is to the left. That's true. Right? So that seems to support the speeding up, slowing down with the plus and minuses. But let me throw another example in here for you. Let's consider this car. And imagine this driver hits the gas, right? And imagine the car's in forward. That means the acceleration of the red car is this way, which is a negative number in this coordinate system. So in that case, the acceleration of the red car would be negative because it's to the left. So you have a negative acceleration, but the car is speeding up. And so there's a counterexample to the other case. And to further confuse it, imagine that the car is moving to the left, but the driver hits the brakes of the red car. That means the acceleration is going to be this way, which is a positive number. So I'll make an entirely different video about interpreting the plus and minus signs. Probably this was not the point to bring it up because this was meant to be an introductory video, but getting back to what velocity or acceleration is, it's the rate that your velocity changes. You'll have an acceleration anytime a velocity is changing. Typically, that'll be an object speeding up or slowing down. However, you can change your velocity without either doing one of those. You can get an acceleration by changes in direction, and again, I'll save that for another video. Typically, units of acceleration in the SI system, it will have units of meter per second. And you'll see this written quite often as meter over second squared. I like this unit. I like to write my accelerations like this, just because I think it best, at least for me, kind of preserves the physical meaning. If this green car, for example, was accelerating at 4 meters per second, right, and it started out with a velocity of 0, and I asked myself, okay, physically, what does that mean? Well, 1 second later, right, the speed is increased by 4 meters per second. Right? So then the velocity of the car would be 4 meters per second. And a second later, 8 meters per second, and then 12 meters per second, and then 16 meters per second, and so forth. So I like to write my acceleration units like this, at least early in a course or early when I'm working with people about these concepts. So, and again, acceleration is a vector quantity. It has a magnitude and a direction. And I'll make a separate video about interpreting plus and minus signs on acceleration. So I hope that this video helps introduce you to this concept. Have a great day.